All right. So we plan to cover 4.1. 4.1 is an overview of chapter 4. So it's very basically summarize what we will do in chapter 4. 4.2, the method of separation of variable. Now this section is about using differential approach to solve the heat diffusion equation. So this involves the solution of partial differential equation, which is a very complicated topic, and we're not going to cover it. Okay, so we will skip 4.2. 4.3, using shape factors and the dimensionless conduction heat rate. We will cover this section. And 4.4, 4.5, these two sections are about finite difference solution. So we will briefly cover these two sections and probably give one or two examples. But for today's outside class quiz, it's about solving a heat transfer problem using finite difference method. So after you go through the 7 questions in the outside class quiz, you will have a pretty good idea about the whole process. Okay? But today, during the lecture, if I have time, I will at least go over one example. So that's the plan for chapter 4. So let's get started to the first topics. The overview of two-dimensional steady-state conduction. To solve a conduction problem, we need the heat diffusion equation. Now this is the heat diffusion equation for two-dimensional because it contains two variables x and y. Steady state because we drop the partial t over partial t, so we drop the transient term, so it's a steady state. Conduction problem with heat generation, so we do allow Q dot to be non-zero, so we don't require Q dot to be zero. So this is a governing equation, and it's subject to different type of boundary condition. The boundary condition of convection, constant temperature, or adiabatic boundary condition. And to solve this 2D problem, there are a few methods available. One is using the analytical method, such as separation of variable. Now, this is a section 4.2, which we will skip. And the other method include the shape factor, for example, which we will talk about it in a minute. And the third method is to use numerical approach to solve the heat equation. So we will also cover it. In particular, we will cover the finite difference method. When we talk about numerical method, there are few choices we can choose. For example, we can choose finite difference method, or finite element method, or finite volume method, and etc. Okay? So there are quite a few numerical approach that allow us to solve the partial differential equation. And this actually is the area of my research interest. So my research work focuses on numerical method for fluid and heat transfer problem. So in the future, if you want to know more about numerical method, you're welcome to talk to me or to email me if you run into any question. The first method using the shape factor. Now, first, let's set up the problem. It's a two-dimensional problem, so the geometry can be a little more complicated. And we have two boundaries, which require these two boundaries have constant temperature. So one is temperature T1, the other temperature is T2. And these T1, T2 have to be constant. So you cannot have half of the boundary to be 20 Celsius, the other half of the boundary to be, let's say, 50 Celsius. You cannot have that situation. the temperature at one boundary had to be constant. At the other boundary had to be also constant, T1, T2. Let's say T1 is greater than T2. Then we expect heat transfer rate from T1 surface to T2 surface. Now, other than these two boundaries, T1 and T2, the rest boundary have to be insulated or at very far away. Okay, so the other boundary have to be insulated or at very far away. So there will be a conceptual question in today's in-class quiz. Ask you, what's the condition for the shape factor method? Okay, so under this assumption, then the heat transfer rate at T1 surface should be equal to the heat transfer rate at T2 surface. It's a constant. Now the heat flux Q double prime at these two surfaces may not be equal. Okay, so know the difference between the heat transfer rate and the heat flux. And we expect the heat transfer rate Q proportional. So this is the notation proportional to the temperature difference. Obviously, if we have a larger temperature difference, T1 minus T2, we will have more heat transfer rate. And if T1 equal to T2, then there will be no heat transfer rate. In addition to the temperature difference, we also know if the thermal conductivity is higher, then heat will be easier to transfer. So it should be proportional to thermal conductivity of the medium, K, as well. So we expect the heat transfer rate to be linearly proportional to K and the temperature difference. Okay? So that's based on the understanding of the conduction. But this is not an equation. To make it an equation, we have to introduce a proportional constant. So let's say K T1 minus T2 multiply a proportional constant. We use a capital S. So this proportional constant S is defined as shape factors. It depends on the shape of the medium as well as the size of the medium. Okay, so this is the shape factor is a geometric property. It doesn't depend on the temperature at the boundary. It doesn't depend on the thermal conductivity of the medium because these two, K and the temperature difference, have already included in the equation. Okay, so this is another conceptual question on today's in-class quiz. So K, the shape factor doesn't depend on the temperature at the boundary. But if you recall, Q can be written in terms of thermal resistance by this equation, T1 minus T2 over the thermal resistance of conduction. Okay, so compare these two equations, we can find the thermal conduction resistance RT comma conduct equal to 1 over Ks. Okay, so that's a relationship between the shape factor S and the thermal resistance R.
Can you just put P2 instead of P1 in that last equation you put there?
Oh, yes, that's a typo. Thank you. Very good. So, again, this is another question will appear on the today's in-class quiz. So remember, that's the relationship between R and the shape factor. Once we have the shape factor, we can determine the thermal resistance of conduction. So the shape factor is for conduction. Okay. So many times they add conduction before shape factor. We don't have shape factor for convection. Okay. The shape factor had to be conduction, and it's the resistance had to be the conduction resistance. Okay. Now let's determine the unit of shape factors. So remember, the shape factor is introduced when we relate Q to K and temperature difference T1, T2. So let's check the unit for each of these variables. K or Q has a unit of watt. K has a unit of watt per meter per Kelvin. temperature difference has a unit of Kelvin. So if you make them equal, and let's use a bracket for the unit of S. So this indicates the unit of S. So now K cancels out, watt cancels out, and the left side is 1. On the right side, it's a unit of S divided by meter. So we require the unit of S, which is the unit of shape factor, to be meter. So the unit for the shape factor is meter. Okay. The few remarks. So we mentioned this is a shape factor is a poor method to get the result quickly. So it allows us to get a approximate result. It's not very accurate because you have to make certain assumptions. For example, the other boundary have to be insulated or very far away. And also, the two surfaces have to have constant temperature. This is, I made this point earlier. And the unit for the shape factor is meter. So again, today's in-class quiz, there will be a question asking you what's the unit for the shape factor. And for actually, we already know, we already can derive the shape factor for some very special configuration. For example, if I have a plane wall with T1 on the left, T2 on the right, and the wall has a thickness L, the thermal conductivity is K. So we know the thermal resistance due to the conduction in the wall is equal to L over K multiplied the cross-section area A. But in terms of shape factor, the conductive resistance is equal to 1 over Ks, right? So compare these two, we find S equal to A over L. So S, the shape factor S for a plane wall is simply equal to A over L. A is the cross-section area of the wall. L is the thickness of the wall. And using the same approach, we can find the shape factor for a cylindrical wall. Okay, so it's 1 over K multiply the thermal conduction resistance. Okay, so this is. So let me show you how did I have this equation. Okay, so if we know the conduction resistance R, we using this equation, the shape factor will be equal to 1 over the conduction resistance multiply thermal conductivity K. So for, let's say, for a spherical wall, if I have a spherical wall, the shape factor for this configuration equal to 1. The thermal resistance of a spherical wall, we know it's equal to 1 over R1 minus 1 over R2 divided by 4 pi K. That's the thermal conduction resistance, multiply K. So K cancels out and equal to 4 pi divided by 1 over R1 minus 1 over R2. So that's the shape factor for a spherical wall. Okay. And I want to emphasize the thermal conductivity K should not appear in the shape factor. Okay? So if you look at the shape factor, it doesn't contain K. That's because K already appeared in this equation. Okay. So, all right. So this is these are the three configurations. The first one is plane wall. Second one is cylindrical wall. Third one is a spherical wall. For other configuration, we have to find the shape factor from table 4.1. So here I include 5 cases. So let's, for example, look at the first case, case 1. Case 1 is for an isothermal sphere buried in a semi-infinite medium. such as ground, a sphere and a ground surface, okay? And the shape factor is given by this formula. Okay? So depending on what application you have, what the configuration you have, you come to this table to find the shape factor. And once you have the shape factor, you can determine the thermal resistance. And then use a circuit to find either temperature or the heat transfer rate. We will have an example in a minute. So let's hold it until we work on that example. So this is about shape factor. There is another approach which allows us to get result quickly, and it's called dimensionless heat transfer rate, Q sub S and star. So that's a dimensionless heat transfer rate. Now the whole idea is based on this fact. So let me show you why we need to introduce this dimensionless heat transfer rate. So for conduction, we know heat transfer rate of conduction equal to the conduction heat flux, which is K multiply the temperature difference divided by the gap between the two boundaries. So that's the heat flux multiply the cross-section area. So now we have the conduction heat transfer rate. Okay. So this is the formula we learned in the first chapter. But for many configurations, such as a sphere inside an infinity domain. So this is the case when you have a sphere of diameter d inside in an infinity domain. We don't have a cross-section. The cross-section area always changes. We don't have a fixed cross-section area. And also we don't have a length L, right? So for this configuration, instead of using the cross-section area and the L, we use a reference cross-section area. We call that active area, A sub S. This is a reference area, okay? And T1 minus T2, those are the same. And we use a reference length, L sub C. L sub C is reference length. But this will not be accurate because A sub C and L, A sub S and L sub C are not the actual area, cross-section area, and the length. So in order to make this to be accurate, we have to multiply some scale factor. And that scale factor is called dimensionless heat transfer rate. Okay? So now, I hope you have you understand why we need to introduce this dimensionless heat transfer rate, because we want to use some reference values, reference cross-section area, reference L, and the reason we need to use reference value because we don't have a fixed L and a fixed cross-section area for certain configuration. Right? So that's why we have to introduce the dimensionless heat transfer rate. Okay, so so this is the equation where we find the Q. So if we know the dimensionless heat transfer rate, know the L sub C, the reference length, and the reference surface, then we can find the heat transfer rate. So let's look at case 12. So this is a case of a sphere embedded in an infinity domain. And the reference length is given by this equation. L sub C equal to the reference surface S sub S divided by 4 pi, and then you take square root. Okay, so let's figure out what is the reference length for case 12. So for case 12, it says the reference area or the active area, A sub S, is equal to pi d squared. So they use the surface of the sphere as the reference cross-section area, which makes sense, right? outside the sphere, the cross-section area will be a function of radius, so it's not constant. But the surface of sphere, that's a constant. So this is A sub s is a constant. L sub c using the formula given here is equal to A sub s divided by 4 pi and take square root. So let's plug into A sub s. So pi d square over 4 pi take square root and equal to d over 2. So that's the reference length, okay, d over 2. So now we also know the dimensionless k transfer rate from this table. It says equal to 1. Okay, it's only equal to number, a numerical value of 1. So, okay, so now to find the heat transfer rate between the surface of the sphere and the infinity domain, this Q will be equal to Q star, the dimensionless heat transfer, multiply the reference cross-section area, multiply T1 minus T2 over L sub C. So that's the formula. Don't forget to include the K, thermal conductivity K. So Q star is equal to 1. K of the medium multiply A sub S is pi d squared, multiply T1 minus T2 over L sub C, which is d over 2, half of the diameter. So we can cancel out one of the d and flip 2. So we have 2k pi multiply d multiply T1 minus T2 over Q. So this is the heat transfer rate between a sphere and an infinity domain. So think about the case of an egg. Let's say we approximate an egg as a sphere with a diameter d and place it in water. Now, let's make a assumption that convection is we only consider conduction. We ignore the convection. In your case, the convection actually is more intensive than conduction. But for the moment, let's assume conduction on it. The egg has a temperature T1. The water has a temperature T2. And the water has a thermal conductivity of K. Now, what's the heat transfer rate assumed at a steady state? Q equal to, using this formula, 2 multiply K of the water multiply pi multiply the diameter of the sphere multiply the temperature difference. Okay, so that's the heat transfer rate. Okay. Now, if I ask you to find the heat flux at, let's say, R equal to d over 2, essentially this is the heat flux at the surface of the sphere, then you have to use Q divided by the surface of the sphere, pi d squared. Okay, but how about the heat flux at R equal to 1 diameter away from the center? You have to use pi 2d squared, right? But remember, in exam 1, one of the multiple choice question asks you to find the relationship between Q prime and the radius. So Q prime multiply R squared equal to constant. Okay. So it's Q prime is inversely proportional to R squared. So this also applies to case 12. So this is about the dimensionless heat transfer rate, Q double prime. Let me see if I have any question in the chat room. Okay, so let's continue. So here is the example. We have a pipeline. It's used for transport of crude oil and is buried in the earth such that its center line is a distance of 1.5 meter. The center line of the pipeline is 1.5 meter below the surface. The pipe has an outer diameter of 0.5. So let me enlarge the picture. Okay. The diameter of the pipeline is 0.5 meter. And there is an insulation layer of 100 millimeter thick. So the insulation layer is 0.1 meter, 100 millimeter is 0.1 meter thick. And the insulation layer is thermal conductivity is given by 0.069. And the ground surface is 0 Celsius. And we want to determine the heat loss per unit length from the pipeline. So we have hot oil inside the pipeline at temperature 120, and the ground is a much lower temperature. So what's the temperature? What's the heat loss due to the temperature difference? Okay. So let's draw the circuit. So in this case, you only need to consider conduction. The convection coefficient is not given, and the temperature is at the surface, not the air temperature. T sub S is the surface temperature. So we can start from the temperature of the pipeline. Let's say that's a T1. I use T sub 1 for the temperature of the pipeline. So T1 equals 120 Celsius. That's the first temperature node. And then we have an insulation layer, which involves conduction. So from T1 to T2, T2 is the temperature of the outer layer. So T2, which is unknown. So T2 is the surface temperature at the outer surface of the insulation layer. So between R1 R2, the conduction resistance is given by the formula of a cylindrical wall, so natural log D2 over D1. D1 is 0.5, so let me use the number, okay? So D2 over D1. D1 is 0.5, so what is D2? What is this D2? So D2 has to be D 0.5 plus 2 times the thickness, okay? Thickness T is 0.1. Now these are the details that you need to pay attention. So, and you only can get familiar to by practicing. Okay, so 0.5 multiply 2 multiply 0.1, so 0.2. So that's a D2. Divide by 2 pi k, we are asked to find the heat loss for 1 meter. So we just make L equal to 1. Okay. So that's a resistance per unit meter. And from T2 to T sub S, that's the resistance which can be calculated using the shape factor S. So that's the resistance of the conduction in the earth, okay? And that we have T sub S equal to 0 Celsius. So by looking at this circuit, in order to find the heat loss for 1 meter, we have to use T1 minus T sub S divided by the total resistance. So let's drop the Q prime. Let's just make sure L equal to 1. Okay. So this Q is for 1 meter length of pipe. So Q equal to T1 minus TS divided by RT conduction of the insulation layer plus the 1 over Ks. And this thermal resistance comes from this equation, okay? And T1 is 120, T sub S is 0. So the only thing we need to figure out is the shape factor S. And also I want you to pay attention about these K, the thermal conductivity. What is the value of this, the first K here? We have two K. One is the K of the insulation layer, 0.069. The other K is the K of the earth or the soil, 0.52. So which K do we use for the first resistance? This has to be K of the insulation layer, okay? And for the thermal resistance associated to the shape factor, this K has to be K of the soil. Okay. So don't confuse these two K, they have different values. Okay, so now we need to determine S. So we go to the table 4.1 and identify the configuration. So this is the configuration we have: a long cylinder and a semi-infinite domain. So the shape factor is given by these two formulas, depend on the condition. The first one, the first one is more general. It doesn't require Z to be larger. The second one requires Z to be greater than 3D over 2. But by looking at these two formulas, both of them involve one function. So I would recommend you just pick the first one because it's not as complicated as it's not complicated at all, right? So you just pick the first one. The first one involves a hyperbolic cosine function. The second one involves a natural log function. Okay. So let's choose the first formula to compute the shape factor.
Wait,
So
Professor,
from the
what was
first,
your reasoning?
Excuse me?
What was the reasoning as to why you chose the top equation over the bottom equation? You said that you had chosen the hyperbolic of cosine over the natural log, and why?
Why? Because if I use the second formula, I have to check this condition. It takes extra effort to verify whether this is correct or not. Okay. But if I choose the first equation, I can ignore this condition because this is more general.
Okay, awesome. So it was all due to the boundary conditions. Okay, awesome. Thank you very much.
You're welcome. Okay. Okay, so let's calculate the shape factor. So it's 2 pi. So when we see L, you just set L equal to 1 meter. Okay. And inverse of hyperbolic cosine. Let's see, 2 multiplied Z. Z is 1.5 meter. That's the distance between the center of pipeline and the surface. Now, what is the value of D we should select? In the figure here, D is the diameter of the cylinder. So which value we should choose for this D? 0.5 or 0.7? What's your choice? Yes, someone answered the question, 0.7. So again, don't make these small mistakes. 0.5, 0.7, it looks small, but it will impact your final result. And you will lose point if you put 0.5 here. Okay. So when you plug it in, I gave you the formula. All you need to do is be careful about the selection of these parameters. If you still make mistake about the selection process, then you will be penalized. Okay. So we're talking about the conduction between the outside of the insulation layer and the ground surface. So we have to use the diameter of the insulation there. And after, now the rest is just a math calculation. So, and I have the numerical value for the shape factor S. When L equal to 1, it's equal to 2.942. And also the heat transfer rate or the heat loss, it's about 84 watt per meter. Okay. And I can further modify this problem by, for example, if I change the boundary condition at the ground. So I say, okay, I have T infinity equal to 0 with convection coefficient equal to 20, for example. So in that case, you will have to add one more resistance. Okay? So now you have T infinity, and you will have a convection resistance. And I also can give you the convection inside the pipeline, and you will have to add the convection resistance. But that's a pretty standard. Okay? The key is to determine the thermal resistance when you need to use the shape factors. Okay, so this is a good example to show the use of shape factor. Now let's let me see if anyone have a question before we switch the gear to a different topics. Anyone have a question for me?
Wait, shouldn't the S be in units of M and not L?
And the answer, okay. So that's per meters. Watt per meter.
No, I mean for the S.
For the S, area has to be equal to 1. So you know, if we are asked for per meter, because I don't want to introduce another notation, S prime. So I will, for this problem, you just make L equal to 1 meters and use Q-based circuit.
What's the unit for Q?
Okay.
Is that Q prime? Or
Prime, what's prime?
like in the final answer?
Final answer, no. If this value will be, let me drop the L because we choose L equal to 1. This S is the shape factor for 1 meter length of the cylinder. Okay. So, you know, I can use Q prime best, but when I use Q prime best, I have to introduce S prime, which is the shape factor per unit length. And basically, there are just too many notations. So, you know, I'm sure quite some of you don't like it. So let's stick to Q-based circuit. So you see here, I don't add a prime for each of the resistance. Okay. So when I calculate the thermal resistance in the insulation layer, I just choose L equal to 1. And when I calculate the S, the shape factor S, I also make L equal to 1. And I understand this Q is the heat transfer rate for 1 meter long of the pipeline. Okay. Okay, so that's a good question. So I hope I answered your question. So now let's switch to the numerical method, which we will only focus on one of the numerical methods. It's called finite difference method. It's a for 2D problem, but I will start with a 1D example. And I'm going to use a plane wall to introduce the finite difference method process. Okay, so let's start with 1D plane wall example, a very simple example. So in the first 3 chapters, when we deal with a plane wall conduction, this is what we do. So we look into a continuous domain. So this is the wall left side, right side, and we assign x coordinate with x equal to 0 corresponding to the left side, x equal to L corresponding to the right side. And at any point x, we can determine the temperature Tx. So Tx is a continuous function. So at any point, you know, x equal to 0.1 or 0.11, 0.1111, whatever point you want, we can have a solution for that. So that's a continuous domain. And we start with a differential equation for the temperature T, and for this case, the differential equation is second order derivative of T plus Q dot over K equal to 0. Right? That's a deduced partial differential equation. Actually, it's an ordinary differential equation. And we also need to impose the boundary condition at the x equal to 0, x equal to L. So those are the two boundaries, and we have to provide boundary condition. And once we have the equation and the boundary condition, we can solve the temperature profile. And this T is a continuous function, which means you can choose any x value, and I will give you the temperature at that x point. Okay. So that's a continuous domain. That's what we learned in the first 3 chapters. Now, to solve the same problem in a discretized domain or discrete domain, what we need to do is we have to decompose the domain into a few nodes. So this is, let's say, x equal to 0. This is x2 equal to L. And we have to divide it into a few node points. For simplicity, I will just divide it into, let's say, 4 node points. You can put more node points. So now I have to introduce a node number. So let's say the first node, I call that m equal to 1. You can use I equal to 1. Or you can make m equal to 0. You say, okay, I prefer the first node to be 0. That's fine. Okay? Just like you can choose x equal to 0 to be your left side, or you can choose x equal to -1 or 1 as your left side. Okay. Second node has to be m plus 1. So in this case, it will be node number 1. This is node number 0, node number 2, 3, and 4. So I have 4 elements, 5 nodes. And we call node 1, 2, and 3. These are the internal nodes. So internal node, in this case, that's node 1, 2, and 3. And the boundary node, which will be 0 and 4. Okay, so if you divide the wall into 4 elements, then you will have 5 nodes with 2 bounded nodes, 3 internal nodes, and each between 2 adjacent nodes, let's say between 0 to 1 or between 1 to 2, there is a space, and we call that delta x. We define that as delta x. That's a spacing. Okay, and the delta x will be equal to the thickness of the wall divided by how many elements you have divided. Okay, so in this case, we have 4 elements. So the spacing delta x will be L divided by 4. So each will be a quarter of the thickness L, right? So this is pretty straightforward. So that's how we introduce a discrete domain. And if you change the number of elements, then you will change the spacing delta x. Okay. So this is a discrete domain. And to solve the temperature, so our objective is to find the temperature at these node points. So numerical solution at T sub m, including T at the first node, T0, T1, T2, T3, and the last node, T4. So we want to solve the temperature at these node points. So it's a discrete solution. We don't have solution between 0, 1. Unlike the continuous solution Tx, x doesn't matter. X can choose any value. But in the discretized domain, we only will be able to find the solution at the node point. So it's a discretized solution, okay? How do we find these solutions? We need an equation. Just like when we solve for the continuous solution Tx, we need a differential equation. To find this discretized temperature at the node point, we need an algebra equation. So the question is, what are those algebra equations? How do we derive those algebra equations? And also we need the boundary condition. We need the node, we need the equation for the node at these two boundaries. So m equal to 0 is the boundary at the left side. M equal to capital N, I make capital N to be the last node, which corresponding to the boundary on the right side. Okay, so I need the boundary condition at these two boundary nodes, and I also need the equation for those internal nodes 1, 2, 3. So we have two equations come from the bounded node, and we need 3 equations come from the internal node. The total we will have 5 equations, and these 5 equations will allow us to find these 5 unknown. Okay, so this is a discretized system. This is a so our objective is to find these 5 equations. So let's see how we can find the algebra equation. There are 2 approaches. I will start with the first approach, which is based on the Taylor expansion. So here I have a graph that shows the temperature T change with respect to x. Let's say this is a function T sub s, but we don't know this function. We only know the temperature, at node point, for example. For the moment, let's say we assume the temperature at this node point to be, let's say this is T at x. We use node M for T at x, and T at x minus delta x, we use node Tm minus 1. And the temperature at this node point, we use Tm plus 1. Okay, so the node point, this is M, this is M plus 1. On the left side, that's M minus 1, right? So according to the Taylor expansion, we have Tx minus delta x is equal to T at x minus delta x multiplied dt over dx plus 1 exclamation delta x minus delta x squared multiplied second order derivative plus high order term. So I hope everyone still remember the Taylor expansion. Right? Otherwise, check your calculus textbook. So at x plus delta x, we do exactly the same, but just change minus delta x to plus delta x. We have Tx plus delta x dt over dx plus 1 over 2 exclamation delta x squared second order derivative of t plus high order term. So now we have those 2 equations. Now let's add these 2 equations. So if I add these 2 equations, on the left side I have Tx minus delta x plus Tx plus delta x. On the right side, I have 2Tx. Now the first order derivative, they cancel out. One is minus, the other is plus, so they cancel out. The second order derivative, minus delta x squared, it becomes plus. So we have 2 plus, and 1 half plus 1 half, so that's 1. Plus high order term. Okay, so we drop the high order term. So now the arranged equation, we have the second order derivative at x equal to T at x minus delta x plus T at x plus delta x minus 2T at x divided by delta x squared. Okay? And using the index notation, using this notation, it just says the second order derivative at node point M is equal to t at x minus delta x, that's t at m minus 1. T at x, that's t sub m. T at x plus delta x, that's t at m plus 1, divided by delta x squared. Okay? So we found an equation for the second order derivative. So now let's go back to this question. What will be the algebra equation for this partial differential equation? We just replace the second order derivative using the result we found. That's a second order derivative plus q dot over k equal to 0. You see, that's a algebra equation connect the temperature at each node point. Okay, and then now we have the 3 equations for the internal node. So let me move it here. So let's say the node point m equal to 1. When m equal to 1, go back to this equation, m minus 1 will be 0. So I have t0 minus 2 multiplied t1 plus t sub 2 divided by delta x squared plus q dot over k equal to 0. And when m equal to 2, 2 minus 1 will become 1. So I have t1 minus 2t2 plus t3 over delta x squared plus q dot over k equal to 0. And m equal to 3, I have t2 minus t23 plus t4 divided by delta x squared plus q dot over k equal to 0. So exactly we have 3 equations for the internal node. And the bounded node depends on the bounded condition. So for the simplest bounded condition, let's say I have a boundary with a, let's make it simple. Let's say this temperature is t equal to, let's make up some number. Okay, so at the surface temperature is 100. At this surface temperature is 60. Okay. If that's the case, then the bounded node, so at the boundary, so T naught, which is the temperature of the first node, will simply equal to 100. And the last node, T sub 4, will be equal to 60. Okay? So basically these are, these 2 nodes, we already know the temperature. So now we reduce the total number of equations into 3 and total number of unknown into 3. So we have 3 equations with 3 unknown T1, T2, T3. Okay? But if I have a different boundary condition, then we will have to solve more equations. So in general, these 2 may not be constant. These 2, but at least we will have 2 equations based on the 2 boundary conditions. So in general, we will have 3 equations for the internal node, 2 equations for the bounded node, and combine those equations, we will be able to solve the temperature at all the node points. Okay. So that's a first approach to derive the algebra equation, and this approach is based on the Taylor expansion. Okay. But for us, I want you to know how to derive the algebra equation based on the energy balance equation. So that this approach is more accurate because it's based on the law of conservation of energy. Okay.
Can you scroll up a bit?
Anyone have a question?
Can you scroll up a bit?
Can I what?
Scroll up a bit.
I didn't get your
Scroll,
question.
can you scroll up a little, move up the screen a little bit.
Move up a little
Yeah,
bit.
there. Yeah, there.
Okay. Oh, yeah. And actually, I can make it full screen. Okay. Thank you for the suggestion. All right. So I want you to know this approach using the energy balance to derive the equation. Okay. So again, this is a plane wall, and let's choose a node point at M. So M is one of the node points. Okay. The left, its neighboring node point is M minus 1. The right neighbor is M plus 1. Okay. And T sub M, T sub M minus 1. Those are temperature at these three node points. And we want to find a relationship between these three temperatures. So what we do is we choose the midpoint between M minus 1 and M. So this is the midpoint. And the midpoint between M and M plus 1. So now we define this shaded area to be our control volume. And we apply the energy balance to this control volume. So let's say conduction heat goes into the control volume and coming out, and also we have heat generation inside the control volume. So that at the steady state, we should have E dot in minus E dot out plus E dot G equal to 0. Okay, at a steady state, we have the stored get to be equal to 0. That's one of the questions on the first exam, right? The stored energy cannot change with respect to time. Okay, so for E dot in, that's the amount of heat goes into the control volume from the left side, and equal to K multiply the temperature at this node point, T sub M minus 1, minus the temperature at the center, T sub M, divided by the distance between these two nodes, which is delta x. Remember the spacing? We use delta x, okay? So delta x is the distance between two adjacent node points. Okay. So K multiply delta T over delta x, that's the heat flux, multiply the area. Let's use A, okay, or A sub C, the cross-section area. So that's a heat transfer rate into the control volume. And for the out is K T sub M minus T sub M plus 1 divided by delta x, multiply the same cross-section area sub C. The heat generation is equal to Q dot multiply the volume, which is equal to A sub C, the area, multiply delta x, equal to 0. Okay? So that's the relationship. So now we can simplify this equation a little bit. First, we can cancel out A sub C, because each term carries A sub C. And then we divide each term by K. And again, we multiply each term by delta x. Okay, so now we have Tm minus 1 minus Tm, another minus Tm coming out, so 2 T sub m. And the minus become plus Q dot delta x squared over K equal to 0, right? So this is the equation based on the energy balance. And if you compare this equation with the one we derived based on the Taylor expansion, they are identical, exactly the same, right? So that's this is a convenient way to derive the algebraic equation. Now for the bounded node, you have to pay special attention. Now, if the temperature at the boundary is constant, then that's a simple case. You just assign the temperature at the node point equal to the constant that provide. Okay, but let's consider a more involved boundary condition. let's say at x equal to L or m equal to node number n. So this is node number n. I have a convection boundary condition with convection coefficient h, flow temperature T sub infinity. So how do I derive an equation for this boundary node T sub n? N is the boundary node. Okay, so don't confuse with internal node. For the example we did earlier, if we choose 4 elements, then n will be equal to 4. Okay, so what we do is we choose a control volume. So this is the middle line, and then this control volume will have a thickness of, what is the thickness of this control volume? If I choose the middle point between two node points, T sub n minus 1, T sub n, what is this thickness? Delta x or 1/2 delta x? What is this thickness? My microphone is too low.
Oh, no. I'm sorry. I wasn't saying that your mic is too low. I was telling whoever was trying to ask you a question, their mic was low.
Okay. Okay, yes, 1/2 delta x. So that this control volume has a thickness of 1/2 delta x, all right? I have to, I will try to speak louder. Okay, so now let's look at the energy balance equation. So we have conduction entered to the control volume by this amount. So K T sub n minus 1 minus T sub n divided by delta x. The distance between these two nodes remains to be delta x. Okay, so divide by delta x, multiply cross-section area A sub C. So this is the conduction heat transfer rate into the control volume, and plus the heat generation, which is Q dot. Now the volume is 1/2 delta x multiply A sub C. So it affects the volume. It's half of the volume that we had earlier. And equal to, minus the heat transfer rate leaving the control volume by the convection. So I want to have the heat transfer rate leaving the control volume to the fluid. So it had to be H multiply T at the node point, at the bounded node, at the surface, which is T sub n, minus T of the fluid, multiply the contact area, which happen to be the cross-section equal to 0. Okay, and you can simplify it to find the equation for the bounded node T sub n. So this is this is how you deal with the bounded condition node. It's a node point T sub n. You have to draw a control volume, and based on the type of bounded condition, apply the energy balance to derive the equation. Okay. So we have the algebra equation, and the last step will be solve this set of algebra equations, which require us to use a solver. And you can use the built-in solver in MATLAB or even Excel. In today's outside class quiz, I will ask you to use Excel to solve the algebra, a set of algebra equations. Once you have solved this algebra equation, then you can have the temperature at the node point. And let me give you some idea about solving the algebra equation. Let's say I have a equation. First equation, let's say T naught equal to some constant 100, and second equation, to make it simple, I have T1 minus the internal node. So this is node M0. For M equal to 1, I have T naught minus 2T1 plus T2 equal to Q dot over K. Let's give a number, let's say minus 1. So M equal to 2, I have T1 minus T2 plus T3 equal to -1. Internal node 3, I have another algebra equation. And the bounded node 4, let me make up an equation based on the, let's say based on the conservation of energy. I found the T4 minus T3 plus T4 equal to, let's say, 2. Okay, let's say 0.5. So I have total 5 equations, and I can write it as a matrix equation, AX equal to B. So A is called the coefficient matrix. So in this case, A is equal to the first equation. Let me define X first. X including the unknown at the node point. So T0, T1, T2, T3, T4. Okay. And B is some constant matrix, which is 100 minus 1 minus 1. So 100 minus 1 minus 1 minus 1.5. So now let's assemble the matrix A. So for T0 equal to 100, I have 1 multiplied T0. So 1, I don't have any T1 in the first equation, so I put 0, 0, 0, 0. For the second equation, I have 1 T0, so I put 1. I have minus 2 T1, so I have put minus 2. I have 1 T2, so I put 1. I don't have T3, T4, so I put 0. For the third equation, I have 1 T1, or 1 T2, no T1, so 1 T2, and minus 2 T3, so minus 2, 1. And the last equation, let's put the last equation. I have no T1, no T2, but also no T0, so 3, 0, and followed by 1 T3, followed by 1 T4. So that's how you assemble the coefficient matrix. And once you have this coefficient matrix, in the Excel you can find the A minus 1, the inverse of this matrix, and use this inverse matrix multiply B, which is get known vector, you get X. So that's a solution process. Okay? So A of the inverse multiply B, you get the known vector X. And the X contains the numerical value of the temperature at these node points. All right, it's time for the in-class quiz. I will add 5 more minutes since it's already 42. So you may want to stay in the room. I want to make sure I covered all the concepts for today's in-class quiz. Right? Let me check the question. So you can start to work on the quiz. I think only one question. Question 8. Ask you to find the relationship between Q double S and Q factor S. I gave you a hint. So you want to compare these two equations, and then you can relate the dimensionless heat transfer rate and the shape factor. Okay. I think that's the only thing that you may need some help.